Hello everyone, welcome back to my channel. So in today's video we'll pick up where we left last time. Okay, so we'll be discussing problem number 1 to 10 from the first paper. So the first question was from units and dimensions. So it said that we have a dimensionless quantity that is constructed in terms of E, epsilon naught, H and C. And they're saying if the dimensionless quantities have so and so exponents, then we have to figure out the ratio of the exponents basically. So essentially the problem is we have to create a dimensionless quantity out of E, epsilon naught, H and C. So H and C, what it reminds me of is the energy of a photon, right? So Hc divided by lambda has the same dimension as energy. So which means H times C has the same dimension as energy multiplied by length, right? Now similarly epsilon naught and E naught, how can we relate it to energy? So we can say 1 by 4 pi epsilon naught times q1 q2, which would be E squared divided by R. This has the same dimension as energy, right? So from here, E square divided by epsilon naught has the same dimension as energy multiplied by length. So if you observe something, Hc has the same dimension as E square by epsilon naught. So we'll just divide both of them. Okay, so if you divide equation 2 with equation number 1, then you'll get this particular quantity over here. And this turns out to be a dimensionless quantity. Okay, so the exponents are in the ratio 2 is to minus 1 is to minus 1 is to minus 1. And in terms of integers, you can just multiply this with n and you'll get the answer as option A. Okay, so now let's move on to the next question. Okay, so this is problem 2 and this is based on Ampere's law. So we have an infinitely long wire that is located on the z axis and it carries a current of I along the plus z direction. Okay, so let's try to plot it first. So the current is in the plus z direction or it is coming out of the page. So we have to find the line integral of the magnetic field along a straight line from minus root 3a comma a to a comma a. So these 2 points lie in the xy plane. So let's just plot them first. Okay, so this is the first point, which is minus root 3a comma a, and this is the second point, which is a comma a. So we have to figure out b dot dl for this path over here. Now again guys, the direction of magnetic field at any general point, you can figure it out using the right hand rule. So the direction will come out to be perpendicular and it will be in the counterclockwise sense as viewed from above, right? So if you observe, if you find out b dot dl and you go from A to B, the sign of B dot dl will turn out to be negative. But in the question, we just want the magnitude. Okay guys, so the first thing is whenever we have a current carrying wire that is coming out of the page, the magnetic field lines, as you may already know, form concentric circles, right? And the direction you can figure out using right hand rule. And the magnitude of the magnetic field, you guys may be familiar with it. It is mu naught I divided by 2 pi r, where r is the radial distance that we're talking about, and the direction is in the theta cap direction. Theta cap is again notation that we use for polar coordinates, which just represents the direction perpendicular to r vector. Okay, so in this case it is just the tangential direction. Now the magnetic field at any general r is in the theta cap direction. So therefore we are going to be performing b dot dl using polar coordinates. Okay, so first let's try to discuss what is dl in polar coordinates. We'll be using this diagram over here. So this is the Cartesian coordinate system and this is the polar coordinate system. So let's say we want to figure out dl elements in a Cartesian coordinate system. So I'm going to start from this point over here and let's say I want to go to this point over here. So one way is to go straight to point 2 and let's call this distance as dl. So this is going to be our dl vector. An alternate way is we can fix the y coordinate and walk in the x direction, a distance of dx, and then we can fix the x coordinate and walk a distance of dy in the y direction. Okay, and hence we can say that dl vector dx I cap plus dy j cap. So this is how we write down the dl element in Cartesian coordinate system. So now if we want to do the same in polar coordinate system, so first let's just choose 2 points. So let's say point 1 is over here. So let's say point number 1 is over here and let's say point number 2 is somewhere over here. And guys, I'm assuming these points are extremely close, by the way. So here the two independent coordinates are r and theta, right? Well, one way again it is to just walk directly to the point and we'll call this as dl vector, and another way is we can walk a distance of dr in the r cap direction and then we can fix r and walk along the tangential direction. And if you observe, the displacement in the tangential direction is r d theta. Okay, so let's just redraw it on the side. So let's say this is the origin and this is point number 1 and let's say this is point number 2 and let's say this is point number 2 and the vector connecting point 1 to point 2 is dl vector. Now let's say guys, this angle, this small angle over here is d theta. Okay, so first in the direction of r we will walk a distance of dr and in the direction of theta we'll walk a distance of r d theta. So this distance is r guys, and similarly even this distance is almost r. So this arc length will have a length of r d theta. So in polar coordinates, the way we write dl is we walk a distance of dr in the r cap direction, and then we walk a distance of r d theta in the theta cap direction. So now as we know the line element, we can just perform integral of b dot dl. So b is mu naught I by 2 pi r in the theta cap direction, dr r cap plus r d theta cap. So this is the advantage of using polar coordinate system. So here, because as the magnetic field is in the theta cap direction, so once we dot theta cap to r cap, that will just give the answer as 0 because these two are orthogonal. And once we dot theta cap to theta cap, that will be just cos 0, right? So this would be mu naught I divided by 2 pi r times r d theta. Now as you guys can see, the term containing the distance r is being cancelled out. So and the final integral, so mu naught I by 2 pi is a constant, and this just becomes integral of d theta. Okay, we'll discuss what integral of d theta is, but this result is simply mu naught I by 2 pi times theta. So this is what the result actually came out to be. Okay, so now what is theta again? So for that, firstly we need a path, right? Because we are integrating over a path. So if I choose this line as our path, which it is in the current problem, so let's take a dl element on the line, which let's say this is our dl element. This was integral of d theta. So what d theta is the angle subtended at the origin by the small element of dl. So this angle is what is d theta. Okay, so now let's say we start from this particular point over here, and as we move towards the right, we keep on adding these small d theta elements, and finally when we reach the other point, the integral d theta will be this total angle over here. Okay, and that is what is written over here. So, and the final answer in this case would simply be mu naught I times this particular angle over here, and that we can easily determine because the y coordinate is a, the x coordinate is also a, so this will be 45 degrees. So let's get rid of this for a second. So this particular length is root 3a, so tan 60 is root 3, so this angle will be 60 degrees. So now, so the combined angle is 105, so this would be 105, and you can either convert it into radians or you can just write the 2 pi as 360, and the final answer will just turn out to be 7 mu naught I divided by 24. So discussing the result a little bit more, let's say I take a parabolic loop, something like this. Now why is the result same even for the parabolic loop? So again, the answer just depends on integral of d theta. So we talked about the angle subtended by this dl element at the origin. Okay, we took it as d theta, right? So this particular angle, we took it as d theta. So now let's say we extend it to our parabola, and let's say this is the small line element of the parabola. So even this dl dash contributes the same angle d theta at the origin as dl. Okay, so once you start adding all the dl elements on the parabola, the angle subtended at the center would be same as the angle subtended by this straight line. And therefore, as the angle subtended is the same, we can say that even the b dot dl along this loop is also the same. Okay, so basically it is independent of r. So you can take any kind of loop on the xy plane as long as it is continuous. The only thing that will determine b dot dl is this angle theta that the line connecting them subtends at the origin. Okay, so that was the discussion for this problem. So now let's move on to the next question. Okay, so problem number 3 is from Oscillations, and we have two beads, each with charge q and mass m, and they are placed on a horizontal frictionless non-conducting circular hoop. So hoop is placed on the table, and it is horizontal and it is non-conducting, and it has a radius of r. Now one of the beads is glued to the hoop at some particular point, and the other one performs small oscillations about its equilibrium position. So let's say the fixed bead is present at the top, so it has a charge of plus q and mass of m, and it's given that the other bead is performing oscillations about its equilibrium position. So guys, obviously the other bead cannot be in equilibrium at this particular position, right? Because the Coulomb force will be repulsive and the normal force will pass through the center, and these are the only two forces acting because gravity is into the plane, right? As you can clearly see, there is a net force in the downward direction, so it will push the bead in the downward direction. Only point where the normal and the electrostatic force are opposing is the bottommost point. So the equilibrium position is actually the bottommost position over here. Okay, so now we'll displace the bead by a very small angle of theta from its equilibrium position. So now we'll connect it to the other bead. Now guys, if this angle is theta, these two particular angles are theta by 2. So the distance between the charges we can easily figure out. So this, if I drop a perpendicular over here, this will be r cos theta by 2, and this will also be r cos theta by 2. So the distance between the charges is 2r cos of theta by 2. Okay, so now we can either use energy method or torque method. So I'll just use the torque method because it's very easy to write the torque in this case. So the electrostatic force will be along the line connecting them, and if I extend this particular line over here, this angle will be theta by 2. So now the radial component of the force is passing through the origin, and so is the normal force, right? So the only component of restoring torque, you could say, above the point O is due to the tangential component of the force, and the tangential component is F sine theta by 2, right? So we can say the net torque above the point O is F sine theta by 2 times the radius of the circular hole, and this would be equal to I alpha, which would be I times minus d square theta upon dt square. Now the reason I'm putting a minus sign here is because the torque is opposite to the direction of theta, right? So the torque or the angular velocity is going to be in a direction such that theta is going to decrease. So we have to put a negative sign over here. Now guys, there is one more thing that is important in this analysis, and which was not provided in the question, okay, and that is that the ring is actually fixed, because if it is not fixed, then the thing is even the ring will oscillate, okay, then the analysis will become really complicated. Okay, so now coming to our differential equation, we can say theta double dot equals, so the Coulomb force is kq1 q2 by r squared, okay, and the value of the moment of inertia of this point particle about the point O is actually mr squared, so we'll just divide it with that as well. Okay, so now we can use a small angle approximation, so we'll set, so sine of theta by 2 we can approximate it as theta by 2, and cos of theta by 2 we can approximate it as roughly 1. So the theta by 2 multiplied with 4 and 4 will give you 32. So the angular acceleration turns out to be proportional to minus theta, just as we expected, and the omega squared, which is the coefficient of theta in this case, turns out to be option B. Okay, so the answer to this question is option B. Okay guys, so in this question we have a block whose mass is 5 kg and it is moving it's moving along the x direction subject to the force of F. So we'll just directly find out the acceleration. It is minus 4x plus 2 meters per second square. Okay, so x is given in meters. At time t equal to 0, it is at rest at position x equals 1 meter. The position and momentum of the particle at this particular time is. Okay, so firstly guys, so this is clearly an SHM, so because a is directly proportional to minus of x, and if you guys are not able to see it, all you have to do is take minus 4 common, and you can see that the internal term becomes x minus half. Okay, and a is nothing but the double derivative of the position. Now this equation is the same as the general differential equation, which is x double dot equals minus omega squared x, but the difference is that here instead of x we have an x minus half. So this is exactly the same, but here the equilibrium position is x equal to half. So if I have to plot it, then as you can see, the equilibrium position where the acceleration is 0 is at x equals half, and it's given that initially it is at rest at position of x equals 1 meter. So the particle is over here at x equals 1 meter and it is at rest. So here the speed of the particle is 0. So clearly the particle is going to move towards the origin, guys, because this is clearly one mean position and it will move towards the equilibrium position, right? So the distance between the extreme position and the equilibrium position is what we call as the amplitude, and that is actually half meters in this case. And we can also comment on the time period of SHM. So that will be 2 pi by omega, and omega is nothing but the square root of this term, which will be 2 seconds. So from here the time period just turns out to be pi seconds, right? So now if the time period is pi seconds, the time it takes to go from the extreme to the mean position is t by 4, which is actually pi by 4, right? So, and they are requesting us things about t equal to pi by 4. So at t equal to pi by 4, the particle will be at x equals 1 by 2. So the answer to the first question is x equals 1 by 2. And then they're asking us about the momentum. So momentum, it's clearly not at rest. So option B won't be correct and option C is correct. Okay, and the velocity at the mean position, we can directly write it as a omega, which is half meters multiplied by 2 radians per second, which is just going to be 1 meters per second. And it will be in the minus I cap direction. So, and the mass of the particle is 5 kg. So if you multiply both of them together, you'll get the momentum as minus 5 kg meters per second. So the answer to this question is option C. Okay, so now let's move on to question 5. Question 5 is pretty standard and it's exactly the question that was asked in JEE 2020. A particle whose mass is m and it is moving in a circular orbit under the influence of a central force, of minus kr, corresponding to the potential energy of kr square by 2, and that we can directly see that if you find minus d by dr of v, you'll actually just get the force, right? Now k is given to be a positive constant and r is the radial distance from the origin. According to the Bohr's quantization rule, the angular momentum of the particle is given by L equals nh by 2 pi, and h over 2 pi, they're just calling it as h cross. So now we have to talk about v and e, which is the speed and the total energy of the particle. So we have a particle that is first of all moving in a circular orbit. The velocity of the particle is actually perpendicular to the radial distance to the particle. And it's given that the particle is actually moving under a central force. So the force is actually in the minus r cap direction and its magnitude is kr. Okay, so first we can write the F equals to ma equation in the radial direction. We can say k multiplied by r equals mv squared divided by r. So we can take the r to the other side and write kr square equals mv squared. And equation number 2 we can obtain from the Bohr's quantization rule. The angular momentum of this particular particle is mv into r perpendicular, which is just r. So this will be mvr and this would be equal to nh cross. Okay, so we'll take the value of v and put it over here. Okay, and once you solve it, you'll get the answer for r square as A option. Now v square would be k by m times r squared. So if you multiply k by m over here, as you can see, it matches with option B. Now option C, they're talking about L. Now L is nothing but mvr, which is actually equal to nh cross. Okay, and nh cross is nothing but r squared multiplied by root of mk, r square times square root of mk. So they're asking us about L divided by mr squared. So if you divide by mr squared by both sides, as you can see, it becomes square root of k by m. So even option C matches. So, and the total energy of the particle will include the potential energy due to the central force, right? So that will be kr squared by 2. And then we'll include the kinetic energy of the particle, so which is half mv squared. So v squared we'll get rid of. So now instead of r squared, we'll put this particular value over here and the answer will turn out to be nh cross by 2 square root of, and for half mv squared also it will be nh cross square root of k by m, and the final answer just turns out to be nh cross square root of k by m, which doesn't match with option D and therefore it is wrong. Okay, so this was a straightforward formula based problem. Okay, so now let's move on to the next question. Okay guys, so now let's move on to question 6. So here we have two uniform strings of mass per unit length, mu and 4 mu, and length of L and 2L, and they're joined at this point O and tied at two fixed ends P and Q. Okay, so while the string will be oscillating, the point P and Q will act like nodes or zero amplitude points. Now it's given that the string is under a uniform tension of T, so we are defining nu naught equals this particular value. Okay, so if you observe this thing, this is the fundamental frequency of oscillation for the first string. In the first harmonic case, or basically in the fundamental mode, we can say that there will be two nodes and the node to node separation is half the wavelength. We can say L equals lambda by 2, and lambda we can write it as a wave speed v upon the frequency of oscillation, and from here we'll get the fundamental frequency as v divided by 2L. Okay, and the value for v for the first string will be square root of T by mu. So this will be 1 by 2L square root of T by mu, and this is what they signified as the frequency nu naught. Okay, so in the first problem statement they're saying if we have a node at the point O, then the minimum frequency of vibration of the composite string is. Okay guys, so for this question, first let's just assume that the entire string is oscillating with a frequency of some f. Okay, now guys, the wavelength of the waves for the left string is going to be the wave speed divided by the frequency of oscillation, right? And if you observe something, the linear mass densities are in the ratio of 1:4, and the wave speed itself is equal to square root of T by mu. So if you observe, the string on the right is 4 times heavier per unit length. So let's say the wave speed of the wave on the left is v, so on the right it will be v by 2, and similar ratio will be followed for the wavelength as well. So if we say the wavelength on the left side is lambda, then on the right side it will be lambda by 2. So because each particle oscillates with the same frequency of f. Okay, so basically when we draw the loops, we have to make sure that lambda of the loops on the left is double the lambda of the loops on the right. And now as we have no information about how many nodes will be there on the left side, let's assume a general case. Okay, so let's take a case something like this. So, and let's say this is the nth harmonic for the left side. Okay, so let's say there are n loops, and for the right loop we have to make sure that the wavelength is actually halved, so there will be multiple loops here. And let's say the right loop is oscillating with m loops. Okay, so or we can also say it is oscillating in its mth harmonic. So now we can say that if there are n loops, each node to node separation is lambda by 2, and if you have n such loops, the separation between point P and point O we can write it as n lambda by 2, and this is equal to the length PO, which is actually L, and lambda I can also write it as v divided by f. So this is equation number 1. And now guys, for the string on the right, the node to node separation is going to be lambda by 4. Why? Because the wavelength on the right side is lambda by 2. So by 2 will be lambda by 4, right? So for the string on the right, we can say m times lambda by 2 divided by 2 equals the separation between O and P, which is actually given to be 2L. From the first equation, we get n equals 2L divided by lambda. And from this equation, we get m equals 8L divided by lambda. Okay, so now we have to take ratio of n and m. So if I take the ratio of n and m, so if I do m by n, this turns out to be 4. What that means is number of loops on the right string should be 4 times the number of loops on the first string. Like for example, in this case, if we take n equals 3, then m has to be 12. Okay, so the minimum possible case will obviously be when n equals 1 and m equals 4, right? So in this case, they are asking us about the frequency of oscillation, so that we can get from equation number 1. So the frequency is just nv by 2l, so that is v divided by 2l, and this is the same value that is given to us as nu 0, right? So okay, so the first option is actually correct. Now in option C also they're asking us about this particular case. So when the composite string vibrates at minimum frequency with the node at O, it has 6 total nodes including the nth nodes. Okay, so we have to count the number of nodes here. So between point P and point O there is one loop, and between the other points there are 4 loops, right? So the number of nodes or zero amplitude points here is 1, 2, 3, 4, 5 and 6. So option C is also correct. Okay, so now for the antinode case, we'll just modify the original case itself. In this situation, point P is a node, point Q is also a node, and the point O is actually an antinode. Okay, so okay guys, so let's say there are n loops on the left side, and the last node to antinode separation is actually lambda by 4. So we can say that the total distance, we can write it as n times lambda by 2 plus the last node to antinode separation, which is going to be lambda by 4. Okay, and for the second case, let's say there are m loops on the right side and similarly another separation of wavelength by 4. So here also it's going to be exactly the same. So here it's going to be m lambda by plus lambda by 4, exactly the same, but here you need to keep in mind the wavelength is actually 1/2, right? So we can say that so if I take lambda by 4 common, I can say lambda by 4 times 2n plus 1 equals L. And if I take lambda by 8 outside from the other side, it will be 2m plus 1 equals 2l. Okay, so now again we'll do the same thing. We'll just take the ratio of these two terms. So we can say 2m plus 1 divided by 2n plus 1 equals 16 by 4, which is actually equal to 4. Okay, and now it must be clear to you guys, the numerator is an odd number, denominator is also an odd number. The ratio of two odd numbers cannot be an even number. So the case we took is a contradiction. So antinode at O is not possible. Okay, so option D would be correct. So there won't be any vibrational mode with an antinode at O, and therefore we can say we can reject option B as well. So the answer to this question is A, C and D. Okay, so now let's do question 7. So question 7 would be from combination of lenses. So in this question we have a glass beaker that has a solid plano-convex base of refractive index of 1.2. So the lens SPUT has a refractive index of 1.6. The radii of curvature of the convex surface is 9 centimeters, while the planar surface acts like a mirror. So the surface SU we have to treat it like a plane mirror. The beaker is filled with a liquid of refractive index N up to the level of QPR. The image of a point object O at a height of h is formed onto itself. So this is a case of autocollimation. So we have to form the image directly at the object itself. Then which of the following options are correct? Okay guys, so let's say this is our lens system. So whenever we are given a combination of lenses guys, if they are thin lenses and the separation between them is 0, then we can separate both the lens assuming a very thin air gap in between both of these lenses. And even for this case, if we do the image formation, the answer comes out to be the same. Assuming a very thin air gap between the lenses does not change our result. Okay, so the refractive index of the fluid is given to be n, and the plano-convex lens is given to be made out of glass, and its refractive index is 1.6. And after that there is also a mirror right in front, and we'll consider a very thin air gap between this lens and the mirror as well. Okay, so now it's given that a point object is placed somewhere along the axis. So firstly it will pass through this lens, it will get processed, then it will pass through this length and it will get processed. If the image and object are formed at the same point, okay, and the mirror right in front is a plane mirror, then the incident rays have to terminate on the plane mirror perpendicularly. Now if it was a curved mirror, then there could be more than one case for which that happens, but if it's a plane mirror, then the rays after being processed have to be incident perpendicularly to the mirror, and after being incident perpendicularly it retraces its path, and the image is again formed at the initial location. So if the rays after being processed by the lens becomes parallel, then what that means is this particular distance is actually equal to the focal length of the combination. Why? Because the light rays from the optics after being incident on the lens becomes parallel after processing. So we'll just find out the focal length for this lens combination. The focal length will equate it to h, and then we'll get the answer. Now guys, these are two lenses that are very thin and they have zero separation between them. So in this case we can say that the equivalent focal length is 1 upon f1 plus 1 upon f2. Now for the first lens we can use the lens maker's formula. So 1 upon f1 would be n minus 1 times 1 upon the first radii of curvature, which is infinity, minus 1 upon the second radii of curvature, which is plus 9, right? So the second radii of curvature is plus 9. And similarly 1 upon f2 will be 1.6 minus 1. The first radii of curvature is 1 by 9 and the second is, so this after solving turns out to be 1.6 minus n divided by 9. So as long as the refractive index of the liquid is less than 1.6, the equivalent lens is a converging lens. Okay, in all the options the value of n is given to be less than 1.6. So now we have the focal length, guys. So we can like get rid of this original lens system and replace it with this symbol. Okay, so what this essentially means is this is a converging lens. Okay, so now after hitting the lens it becomes parallel. Okay, so which basically means the distance of the object from the lens is equal to the focal length. Okay, but the geometrical distance between the point O and the lens was given to be equal to h. So this is the equivalent focal length. So instead of writing f equivalent, I can also write it as h. So h just becomes 9 divided by 1.6 minus n. So now we have to substitute all the values of n inside here. Okay, so once you substitute all the values in, only option A and B will match. Okay, so the answer to this question will be A and B. Okay, so now let's move to the next question. So this is problem number 8. So the specific heat capacity of a substance is temperature dependent and it is given by this particular formula. Okay, and everything is given in terms of SI units. So they're saying if the heat required to rise the temperature of 1 kg of the substance from 200 Kelvin to 300 Kelvin is nk, then what is the value of n? So if I have a system, guys, whose temperature is T, and if I want to raise the temperature by T plus dt, a very slight amount, then the small heat that I would have to provide is mc dt. Okay, so now for the total heat we'll just integrate this expression. So we'll get Q equals integral of m times c dt. This just simplifies as this expression. So m is 1 kg, so this will be k times 300 squared minus 200 squared. So this will be 9 minus 4 5, so 50,000 by 2 will be 25,000 k. Okay, so this would be the answer to this question. So this is problem number 9. It's from rotational mechanics. So we have a disk whose mass is m and radius is r, and it is free to rotate about a vertical axis as shown in the figure. Okay, a battery operated motor of negligible mass is fixed to this disk at the point on its circumference. Okay, so the motor is kept on the circumference of this bigger disk and it is right under the smaller disk. Another disk whose mass is capital M itself and radius is r by 2 is fixed to the motor's thin shaft. So you can, I mean, from the side view, if you want to observe, so this is going to be the bigger disk and then we have a motor here and then the smaller disk is attached to it, something like this. Okay, so you can imagine it like that. So the motor is now switched on so that the smaller disk rotates at a uniform angular speed of omega. If the angular speed at which the larger disk rotates is omega by n, then the value of n is going to be. So we have to find the omega of the bigger disk. Yeah, this last line over here, guys, that the smaller disk rotates at a uniform angular speed of omega, this can be perceived in two ways. So either the omega can be the omega with respect to the rotating frame, or it can be the omega with respect to the ground frame observer. So I'll explain what those two actually mean, analyze both of the situations separately. So now let's begin with the solution. Okay, so first let's discuss why is the angular momentum conserved in this case. Let's say this is the bigger disk, okay, and let's say this red thing is the motor that is attached to the bigger disk. I am drawing it big so that I can explain the point, okay, but it's actually tiny. So now there will be some shaft from the motor, and to this shaft we are attaching another small disk, something like this. So now guys, the shaft is not rigidly attached to the motor. Okay, so if the motor applies an internal torque will the shaft start rotating. Okay, so now why is the angular momentum conserved in this case? And for that we can observe the shaft plus the disk and the motor separately. So the motor definitely will apply some kind of torque tau, let's say in the plus k cap direction. Okay, so by Newton's third law we can say that the shaft will apply a torque of minus tau in the opposite direction. Okay, and this minus tau and this torque is actually a coupled torque. Okay, so it's the same about any particular axis. So even about this vertical axis, there is going to be a torque in the minus k cap direction. Now if if the torque term confuses you, then what you can do is you can break it down into two coupled forces. So we can also say that there is a force of F that is acting into the plane on the right side and a force of F that is acting out of the plane in the left side. If you curl your fingers, you can see that even in this case, the moment is still in the k cap direction. Now by Newton's third law, you can again say that the force acting on the right end on the motor, F out of the plane, and on the left end, it is F into the plane. So now observe the torque above the center of mass. So clearly the torque due to the further force is greater, right? So which means the torque is going to be in the minus k cap direction. So basically, if the couple force applied by the motor on the shaft is in the k cap direction, then the reaction pair applied by the shaft on the motor is in the minus k cap direction. Okay, and because of that, the omega of the disk will be in the minus k cap direction. So that's a little bit about why the net torque, taking both of them at the same time, is actually 0. And it will be 0 about any axis. So even if you take this axis, still the net torque is 0. Even if you take this axis, the net torque is 0. The choice is up to you. So we'll just be using this fixed axis attached to the bigger disk, and we can say that the angular momentum of disk number 1 plus the angular momentum of disk number 2 about this axis, we can say it is conserved. Okay, so let's say we take the normal Cartesian coordinate system, guys, and let's say we have some kind of object over here whose center of mass is moving with a velocity of vcm, and above the center of mass axis, the rigid body is rotating with an angular velocity of omega. And if you want to write the angular momentum of this rigid body about the origin O, then the result turns out to be, if you first treat the center of mass like a particle, so it will be m rcm cross vcm. Okay, and then assume that the object is performing fixed axis rotation about its center of mass. So that will be ICM multiplied by omega. So this is the general result for writing the angular momentum of a rigid body about any fixed origin. Okay, so again here we are talking about the ground frame. So x and y axis are remaining fixed. This omega over here, we are reporting it with respect to the ground frame again. Now if we start rotating the coordinate system according to this reference frame, the omega is not going to be this particular omega. The omega that will be perceived by this frame is going to be different than this omega, and we'll take the help of an example to understand this. So basically, for this formula to work, the coordinate system must be an inertial frame of reference and the point O must be fixed. Okay guys, so now we are going to take the help of a situation, understand how omega is different from the rotating frame and the ground frame. So let's say, guys, so first let's talk about the ground frame. Okay, so first let's talk about the ground frame observer. So now once again, guys, what is the situation? So we have a rotating turntable, and then we have a rod that is rigidly attached to the turntable, and on the rod we mounted a disc, something like this, which is free to rotate about its own axis. Okay, so unless and until somebody from outside applies a torque on it, this disc won't rotate. Okay, so now let's look at the top view. Okay, so this is the top view of the situation, guys. So just so we can identify different cases, I'm going to draw a square on top of this disc. Okay, so from the side view it will look something like this. So from the side view, the square will look something like this. So it is directly on the line connecting these two black points. Okay, so now what we're going to do is we're going to start rotating the turntable with some angular velocity of omega. So guys, what will happen is, as I said, the pink disc cannot rotate about its own axis. So when the turntable rotates by 90 degree, this is the situation that will happen. The line connecting the square and the center will still be horizontal. As you can see, it was horizontal initially. Finally also it will be horizontal. And that's the reason for that is it's because it's not rotating about its own axis. If the pink disc was rigidly attached to the green disc, then when it comes to the top, this square will be at the bottom. But here in this case it is not rigidly attached, right? So this will be the case, and this is what we call as pure translation. Any horizontal line you draw on the rigid body, it will always be horizontal in this case. So we can say that this disc over here, it is performing translational motion. It is not rotating. If it was rotating, then this horizontal line connecting the square and the center will also start to rotate. So with respect to the ground frame observer, he will say that disk is performing translational motion. Why? Because the orientation is always maintained. It is always horizontal. And when this happens, this is what we call as curvilinear motion, or just translation. So according to the ground frame observer, the omega of the pink disk will be 0. Because it's not rotating. Okay, so now let's take a different observer. So let's say we make a guy sit on the turntable so that his head is rotating with the same angular velocity as the turntable, and this is what we call as a rotating frame of reference. So basically this guy's head is looking at the square initially, and as the disc starts moving on the turntable, his head will also start moving. Right? So if you ask this guy, he will say initially the square is right in front of his eyes, but when the table has rotated by 90 degrees, now the square is not right in front of him. In fact, he would say that the square has rotated by 90 degrees in the clockwise direction. So according to this guy, the pink disk has an omega which is the same as the omega of the turntable, but it is in the opposite direction. So what I'm trying to say is the table rotated by 90 degrees in the counterclockwise direction, right? But the square, as you can see, it rotated by 90 degrees in the clockwise direction. According to this guy, he will say that the pink disk is rotating with an angular velocity of minus omega. So here it was omega in the counterclockwise, and here omega is in the clockwise direction. So the omega of the pink disk, according to the rotating frame guy, he will say that it is minus omega. Okay, now guys, what is the omega of the rotating frame? It is simply omega, right? It is omega in the k cap direction. This is the relative omega and this is the omega of the frame. So if you add both of them, you'll get the ground frame omega, which is exactly 0. Okay, and this matches with the ground frame observer. Okay, so this is how omegas are kind of different depending upon the frame of reference that we choose. So the guy sitting on the turntable observes the pink disk to be rotating, and the guy on the ground frame will say that it is just translating. Okay, so now what happens if I give this pink disk a spin? Okay, so let's say some guy from the outside gave it a spin. So if I give it an external spin, guys, I'll just vectorially add omega spin to each of these cases. According to the ground frame observer, the omega of the disk was 0, right? And now we'll just vectorially add omega spin. And now according to the ground frame guy, the omega of the disk is equal to the spin omega. Now the rotating frame guy, so here also let's just first add omega spin vectorially. So I gave the spin in the clockwise direction. Okay, so now the rotating frame guy will say that it is spinning. It has a spinning omega, but it also has a minus omega, right? Now according to the rotating frame of reference, the omega becomes the spin omega minus the omega of the frame. So this is the idea that I am trying to discuss. So if I just want the magnitudes, it will be spinning omega, which is in the minus k cap direction, okay, minus the frame omega. Frame omega is in the k cap direction, so which is omega k cap. Omega spin plus omega in the minus k cap direction. So this is what the rotating frame of reference will observe. So basically, if the ground frame observer observes the spinning omega to be omega spin, then the rotating frame will observe it to be omega spin minus omega of the frame. So now we can apply this to the given problem, and let's just see what happens. Okay, so this is the given case to us, guys. So let's just assume that the omega of the disk. Now in the question, guys, they just mentioned that the angular velocity of the small disk is equal to small omega. They did not mention if it is from the ground frame or the rotating frame, even though 99% chance is that they probably meant the ground frame. So if it is the ground frame, then it's pretty simple, right? So let's assume this is omega. So now we discussed that a torque will act on the bigger disk, which is in the opposite sense. So its angular velocity will be something else. Let's call it capital omega, and it will be in the clockwise sense as viewed from above. And this is in the counterclockwise sense as viewed from above. So now we'll just apply angular momentum conservation. So this bigger disk is just performing fixed axis rotation about its own axis. So we can say its angular momentum, moment of inertia, which is mr square by 2 for a disk, times capital omega. And the direction again is in the minus k cap direction. So I'm assuming the vertically upward direction as k cap. Okay, now this is the angular momentum of the bigger disk. Okay, now let's write the angular momentum of the smaller disk. So the smaller disk is it's performing fixed axis rotation and translation at the same time, right? So we'll use the general formula. So we'll use this formula over here for this case. So the center of mass, guys, it will move in a horizontal circle, right? And the velocity of the center of mass, it will be into the plane, and it will be equal to capital omega multiplied by this distance, which is nothing but the radius of the biggest disk. So this will be capital omega multiplied by r. So this is going to be m RCM cross VCM. VCM is into the plane, RCM is in the minus x cap direction. If you curl your fingers, then you'll get the direction as minus k cap. So this will be m r square capital omega in the minus k cap direction. Okay, so now this is term number 1, and term number 2 is the fixed axis rotation term. So about its own axis, the angular momentum of the smaller disk is, okay, there won't be a half here, guys. I made a mistake. So there won't be a half here. Angular momentum is going to be ICM, which is m times radius squared by 2 times small omega. And this, if you observe, is in the k cap direction. This is the net angular momentum of the system right after the motor started to spin and just before it was equal to 0. And this, after you solve, capital omega turns out to be omega divided by 12, which is what most people would have written the answer as. Okay, so this would be case number 1. Okay, so the second possible case is that the angular velocity of the disk, which they gave as omega, is with respect to the rotating frame of reference. Okay, this is with respect to the rotating frame of reference. So the rotating frame of reference omega is a spin omega minus the omega of the frame. So which means this omega that they gave is the actual spinning omega, which in this case, let's say it is in the k cap direction, minus the omega of the turntable. Okay, so this will be omega spin in the k cap direction. The omega of the turntable. The omega of the turntable is capital ohm in the minus k cap direction, right? So this will be minus ohm k cap. So I'm assuming omega to be in the k cap direction. So from here we can see that omega spin is equal to omega minus capital omega in the k cap direction. Basically, in our angular momentum conservation equation, this omega is actually the spin omega, or you could say the omega that the ground frame guy sees, right? So basically, if I assume that the omega given to us was with respect to the rotating frame, then this is the spin omega. So then we have to substitute, instead of omega in this expression, small omega minus capital omega. Or we can also substitute this into this expression over here, and from here we'll get capital omega as small omega by 13. So this is the second possible answer. So these are the two possible cases that could happen in this question, guys, but most probably they'll just give this as the answer. Okay, and yeah, so that's about it for this question. So now let's move on to the next. Alright, so this question is based on polarization. So we have a point source S that emits unpolarized light uniformly in all directions. At 2 points A and B, the ratio IA divided by IB, which is basically the intensities of light, is actually 2. So now if a set of Polaroids having 45-degree angle between their pass axes is placed just before the point B, then the new value of R will be. Okay, so this is a direct problem from Malice's law, guys. So let's say this point O is where the point source is kept. Now the intensity at point A is greater, right? It is greater, so which means the point A is closer to the origin. The point A will be somewhere over here, and let's say the point B is somewhere over here. So now the intensity, guys, in the case of a point source is the power of the source divided by 4 pi r squared. Or we can also say it decays as 1 by r squared, which means if the intensity ratio IA by IB is 2, then this is also the ratio of the square of the distances, right? So RB will be root 2 times further away from the point O. So basically, if this distance is smaller, this distance will be root 2r. So now they're saying we keep two Polaroids right before the point B. So obviously what will happen is that the intensity of the light reaching point B will change. So let's just say that the original intensity appearing at point B was IB. So now we have to see what happens to IB. Okay, so firstly, if I keep a Polaroid and we send unpolarized light passing through it, emergent light ray will first be parallel to its transmission axis and its intensity would become halved. This is what Malice's law states, right? So the initial incident intensity is IB. So after being processing by Polaroid number 1, it will become IB by 2. Now the polarized light ray of IB by 2 is passed through another polarizer whose pass axis or transmission axis is at an angle of 45 degrees to the incident light ray. So we can say that the emergent intensity, let's call it IB dash, it will be equal to the incident intensity and it will decrease by a factor of cos square theta. And this would be nothing but IB by 2 times cos square of 45 would be half. So this becomes IB divided by 4. So basically, after being processed by two of the Polaroids, the intensity at the point B decreases by a factor of 4. So now we have to talk about what happens to the intensity ratio IA divided by IB. Now obviously, guys, IA is not changing. IB reduced by a factor of 4. So R will actually become 4x, which basically means 4 times the original value 2. So the new value of R will be simply 8. Okay, so that is the answer to this question. Okay, guys, so that was all the problems of paper 1. So now we'll discuss paper 2 in the future videos. And if you guys have any doubts, you can comment down below. And if you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.